Normal probability plotting is a graphical tool that helps us examine whether a data set follows a normal distribution or not. So if you got a random sample of data points, you want to check whether the data follows a normal distribution or randomly distributed. Okay, so you can use normal probability plotting. So normal probability plotting is based on the fundamental idea of linear rectification. So the idea is to transform a nonlinear function into a linear one. So suppose there is a nonlinear function q equals to alpha sk. You see here, q is the response variable, and s is the predictive variable. Alpha and k are the parameters to be estimated. So if you take the log on both sides, you see here, and this multiplication alpha multiply s power k will become log alpha plus log sk. And then you put this k over here. So it will become a linear function here. So the nonlinear function is transformed into a linear function, log q as the response variable, log s as x, and this k is the slope, and the log alpha becomes the intercept. Okay, so this is y equals to ax plus b. So if we plot y versus x, we know that we can estimate the slope by doing the, if we know 2 points, then we know the a is actually y2 minus y1 divided by x2 minus x1. So that is delta y over delta x. So this will give you the a. And also, if you find the intercept of this line versus the y-axis, you got the b. And this is the minus b over a, the intercept with the x-axis. So in this way, if you plot log q versus log s, and you know that log alpha will be intercept with the y-axis with the log q axis, right? And then minus log alpha over k. So this is minus b over a, log alpha over k. So you know what is the k and you know what is the log alpha by find out these 2 intercept points, okay? So in this way, you transform the nonlinear function into the linear function, and then by drawing the linear line and in the log q log s axis, and then you will be able to find or estimate this parameter alpha and the k. So how to apply this idea to the normal distribution? We know that x is a normal random variable, then z, we can standardize this normal random variable with x minus mu over sigma. And this is the z. Z is a standard normal random variable. And we know if this is the inverse of the cumulative distribution function, we know that a phi inverse f, if we know the cumulative probability function, then if we do the inverse, we will get the z, right? So x minus mu over sigma equals to phi inverse f. So if we transform this, move this sigma to the right-hand side, and then move the minus mu to the other side, it will become x equals to sigma phi inverse f plus mu, okay? So this is a nonlinear function, but based on the inverse, phi inverse, and based on the standard normalization, standard normal random variable, and we convert the nonlinear function into a linear function. So the response variable will become x, and the predictive variable, it will become phi inverse f. So we are going to plot x versus phi inverse f. Then it should be, if x is a normal random variable, then this should be approximately linearly, a linear line. So for the data set x1 to xn, we construct normal probability plotting as follows. First, if you have all the x, you sort the data from the smallest to the largest. So original index is x1, xn. Now you sort it from smallest to the largest, you give a new index. So here the parentheses indicate the new index in the ordered data set. And then we can estimate the CDF value for each the ordered data set. So for x, for example, this is x1, then it will become 1 minus 0.3 divided by n plus 0.4. So this equation is given by the book, and also many statisticians are doing the numerical studies and theoretical studies to find out what is the best way to estimate the f. And after sorting the data from the smallest to the largest, they found out this is the best way to approximate the cumulative distribution, cumulative probability. So where I is the index of xi in the ordered data, n is the total sample size. Then we know the cumulative probability, then we do the phi inverse, and then we plot xi, the ordered data set, versus this phi inverse f. And then check whether there is a straight line between this xi and phi inverse f. So if the data follows the normal distribution, then there should be an approximately straight line. And if you plot this straight line, then you can estimate the slope and the intercept, estimate the parameters mu and mu hat and the sigma hat through the slope and the intercept of the straight line. So fundamental idea is the linear rectification. So here is a MATLAB software demo, and we can generate the data set. And but this is a simulated data set, so it's a normal random variable 2 and 4. We generate about 500 data points, 1 by 500. But in the real world case study, you might got a bunch of data points. You can use your real data here, okay? So the sample size is the length x is 500, and we sort this x from the smallest to the largest, and then the f inverse, right? The probability sort is I minus 0.3 divided by n plus 0.4, and then we phi inverse this f. So norm inverse this f 0 and 1. So this is a standard normal random variable inverse, phi inverse. And then we plot this x versus this, this sorted x, not this original x, okay? We plotted the sorted phi inverse versus phi inverse here, phi inverse f, and sorted x in the y-axis. So this is x-axis, y-axis. We plotted it. So the normal random, those normal randomly distributed data will follow approximately a straight line. And then this is a way to check whether the data is normally distributed or not. So that is a normal probability plotting. And you can try these commands in the MATLAB. You will get approximately this plot. So that's how we generate normal probability plotting.